Hi, everybody. My name is Paul Luce. I am happy to be here today to share with you some information about the new SPDK accelerator framework. It's faster than a cheetah and more flexible than a Cirque du Soleil performer. You're going to find out why I chose such a cool title after we get through the material, if I've done my job right. So the accelerator framework has been something that has been in the works here for well over 18 months. Lots of folks have made contributions, and we're finally to the point where there's enough new stuff that it kind of warrants an entire talk to both educate and inform the rest of the community and maybe solicit some more input and contributions from folks as well, because it is some pretty cool stuff. Okay, so first we're going to talk about the high-level architecture, not really spending more than a couple of seconds there, just so you see where the accelerator framework fits in. And then a little bit of history of the original copy engine and where that fit, what it did, and then we'll just mold right into the new requirements, right? Where did we go from the copy engine? Why did we get to the accelerator framework? And why did we do all this work? And then a quick deep dive on the Intel data streaming accelerator module as an example of a Excel framework module to give you, something a little more concrete to look at and understand. All right, so here is our typical SPDK architecture slide. You can see it's pretty busy. We've got so many features and new blocks and new modules to put in here that they're kind of categorized here. This actually doesn't include absolutely everything, but it's a lot. And you can see here is the accelerator framework, just so you know where it fits in. Falls in under services. It's available to pretty much any other module within SPDK, all of its capabilities. Now here's our blast in the past, the original copy engine. Right? You can see back in 2016, our architecture diagram was not nearly as busy as it is today. Like I said, that previous one doesn't even include everything that we do anymore. We just can't get it all on one page. But here's what we looked like back in 2016. Can you see where the copy engine is? I bet there are a few of you that can. Oh, there it is. It's the Intel Quick Assist Technology driver. Right. So the copy engine actually wasn't really a framework. It was an implementation of the IoT driver with a bit of abstraction in it, so that if you were to call the copy engine's copy or fill functions, the top level APIs, that if you had the IoT driver enabled and running, it would use IoT to do those operations. If not, it would use software. Okay, which brings us to the requirements that drove the accelerator framework. And first and foremost, right, we wanted to build on what the copy engine was doing and what it was developed for, right, to provide a set of generic APIs for accelerators that allow developers to just write to one API. And then what it did behind the scenes is a function of the features and the capabilities of the accelerator framework itself. And that's why we're going to be going through it today. Next big one was the coming of a new hardware offload module, the data streaming accelerator, a DSA thing from Intel. It was going to add a bunch more operations besides copy and fill. It does CRC32, dual cast. You're going to see a bunch of them later on. So we came to this point where, okay, we have to make the copy engine do more than IoT. So let's actually give it a real facelift and make it extensible and make it really easy for new hardware, Excel framework hardware modules to be written and plugged in. And you'll see the flexibility coming up here in a couple slides. Another one was the introduction of virtual block devices for crypto and compression that directly use DPDK interfaces from the block device layer. Okay, so some of you may recall these have been around for probably 3 years. Right before the accelerator framework, we have a compress virtual block device and a crypto virtual block device. Those are standalone modules that don't interact with anybody else in terms of getting their crypto capability functions, except for DPDK, right? So compression uses the compressDev API, and that's all built into the virtual block device module, and crypto uses the CryptoDev API from DPDK that's plugged into the BBDev crypto module. And then you use RPCs against those virtual block device modules to pass parameters and set up, which pulled mode driver you want to use and all that kind of stuff. Well, that kind of, as soon as we started to build up the accelerator framework, lots of people, I think at the same time, noticed, geez, we've got accelerator stuff hard-coded in the virtual block devices, and yet we've got another place where we're doing accelerator stuff. Maybe we should consolidate all this. So having those there helped drive the need to make the accelerator framework bigger, more robust, and more extensible. And you'll see what we're doing with the BBDevs and the accelerator framework here in just a second. And then last but not least, the introduction to the IPU, the infrastructure processing unit, is likely to introduce new offloads. So again, I've got one slide on IPU next. We're not going to talk about that too intensely, but we felt like with that becoming really popular out there in the industry, there's going to be more and more folks wanting to write accelerator modules for that particular use case. So we had better have a decent place, decent framework to land those modules. All right, as promised, there's your super high-level IPU diagram. And you can see here over on the left, we've got our host CPU doing all of its regular stuff. And then the IPU, which is essentially a system on a chip, right? It's an offload capability, offloading some networking stuff. And of course, we're going to put storage in there, and that's where SPDK plays. SPDK is basically the storage plane for IPUs, right? So SPDK is running in firmware on this IPU and emulating an NVMe Express device over PCI back to the host CPU. And then it gets its storage. It can get it locally if that's available, or it can go out using the NVMe initiator and get storage off box, right? So why would we think this is going to introduce more offload capabilities? Well, this IPU is typically not the same kind of horsepower as this CPU, right? So it only makes sense, right? You want your IPU focusing on, fundamental processing of IOs and not mundane tasks like, copy and CRC32 and a bunch of others that are coming into play. So that's really why, right? This is a big home for SPDK. Okay, so let's take a little bit closer look at the accelerator framework, and we'll jump even deeper into it a little bit later on. As you can probably tell, this is the big picture, right? This is all of SPDK, and this is just showing the next level down. Here's the accelerator framework. Here are the available modules that we have today. We have DSA, the data streaming accelerator. We have IAA, this is brand new. This is the Intel Analytics Accelerator that does some compression, decompression. We have IOAT, the original guy. And then you can see I have in work in progress, we have QAT and Mellanox, and I'll talk about those in some upcoming slides. These are directly related to getting those hard-coded compression and crypto APIs out of the virtual block devices and having the virtual block devices use the accelerator framework instead. And then I have ICE-L/software, right? So this is essentially the software module, right? If you don't have any hardware modules that are capable of processing the incoming operation, we'll pass it to the software module, which is its own file now. It used to be kind of all lumped in together. That was part of the refactoring of the original copy engine and the growth of the accelerator framework. But the Excel software module will use ICE-L where appropriate for compression and crypto and CRC32. And if it doesn't have anything fancier, like a memcopy, or for a copy, it'll use memcopy. For a fill, it'll use memset, that kind of stuff. So basic software functions where ICE-L can't optimize. All right, next dive into this thing. On the left-hand side, we've got the SPDK application or library. And then up here, I've got some sample APIs that go to the accelerator framework. So you can see they all follow this pretty basic naming convention. They start with SPDK, Excel, and then you're submitting Excel, and then you're submitting 2C. So I think we have 7 of them right now, but they all filter into the accelerator framework. Now, before I start walking through a couple of animated arrows here, let's talk about what's down below. Okay, now down below, we have a DSA public low-level library, right? So think of this as the device driver, right? This is actually responsible for initializing and interacting with the hardware. So that's what we call the low-level library. We have one for IOAT as well, right? And you can see the APIs that are available also to the application. If they want to bypass the accelerator framework, they could call SPDK IDXD submit copy, and that goes to DSA. And right, unless you're really into the weeds with some of us, you're going to wonder, why does it say IDXD submit copy and this says DSA? IDXD is something that we sort of inherited from the kernel driver that supports DSA. It stands for Intel Device Accelerator Device Driver. I don't know what it stands for. But DSA stands for DSA and IAA stands for IAA. They both share this low-level library that is sort of a generic term for Intel accelerator devices. So if somebody wanted to, they could call directly into the low-level library for DSA. Same thing with IOAT. They can call IOAT library directly and bypass all this stuff. Why would you want to do that? Well, I'll talk about that on an upcoming slide. But let's walk through what happens here, right? So let's say I submit one of these calls and it goes to the accelerator framework. The accelerator framework is going to look and see what modules are available, what hardware is initialized, what can I do with this thing, where should I send this call? In this case, it's going to send it to the software module, right? So in this case, whatever this was, depending on where it wants to go. Let's say it says, oh, I've got DSA module loaded and this command should be routed there. The accelerator framework is going to, with its DSA module, which by the way is a sort of a plugin. It's not really a device driver. It's a plug-in shim between the accelerator framework and the low-level library. The DSA module will then call the low-level library using the same exact API that the application or library could do if they wanted to call it themselves. So that's kind of a nice feature for us, right? We don't have any weird backdoors between the accelerator framework and the low-level API. All the same stuff. So you might ask, well, why do I have this? So I've got a slide coming up on that. Besides the obvious generic API, instead of having to write to the hardware, there's some other benefits of using the accelerator framework and the modules as well. And then same thing, if it were IOET, the framework would then route it to the IOET low-level. All right, here's the flexible part, right? Here's the Cirque du Soleil part. Okay, so here's the framework again, and same API examples over here. Again, there's like 7 of them. I just listed 3. Copy, fill, CRC32. We basically have a simple mapping table in the accelerator framework where you've got the commands and you've got the available modules. I'll talk about how those are assigned a little more detail in the next couple slides, but by default, they're all just assigned by the order in which they're initialized. So you can see in this example, these first 5 operations are all mapped to DSA, and the compress operation is mapped to QAT, and encrypt, decrypt are mapped to the Mellanox module. So as obvious as it looks, right, if a copy were to come in, the accelerator framework would know exactly where to send it. Okay, so what if you want to change that, right? What if you don't like the fact that it was initialized by the order in which these modules came up? Well, now we've got a couple of RPCs and APIs that allow developers and system administrators to really control how this thing works. Okay, so module discovery starts off with here's the API. You can go and get your module name, and then you can also go and get module info. Right. So here's some examples on the right-hand side. When you get your module name, your request. This is actually the info. You request your get info, and then you can see on your response, it'll tell you, oh, I've got a software module, and this is sort of legacy name is engine. It's actually should say module. I think we've updated the code. I just never updated the slide. So it'll say you have a software module, and here's a list of its supported operations, and you have a DSA module, and here's a list of its supported operations. Okay, so if I'm a system administrator, I can simply use an RPC to figure out, what I have available and how do I want to configure the system. So the next obvious step after you've identified what's available, you have to actually make some assignments. And again, we can do this via the C API, which is a simple assign opcode, and you assign an opcode to a module, or through the RPC. You can see right here, we've got assign opcode, and we'll say the method here is assign opcode, and my parameters are I want to assign the copy operation to the engine of the module, software module, and if that's available, it's going to go ahead and say true, right? And there's 2 things that have to be true in order for this call to work, right? Number 1, the module has to be present, right? Now, the software module is always present, but let's say I tried to do this for DSA and my machine doesn't have DSA in it. Well, it's going to come back and say false, right? I couldn't do that for you. I didn't tell you why. And the second condition is not only does the module have to be present, but it has to support the operation you're trying to map to it, right? So if I tried to support dual cast, if I tried to assign that to IOET, it's going to come back and say, okay, your IOET is loaded, but it doesn't support dual cast. It doesn't know what to do with that. So it's going to come back and fail, right? So this allows either the programmer or the system administrator to, completely configure how these opcodes are mapped to which modules. All right, so let's talk a little bit about DSA. Now, this slide is nothing to do with SPDK. This is just DSA. But the key point here is DSA was designed for user space applications to use it. So without going into a lot of detail on this, we've got a kernel driver that is always responsible for initializing the hardware. And then you've got some external methods for creating work queues, right? So obviously the kernel can create work queues on its own and make those available for use by other kernel modules. But there's also user space tools that say, hey, kernel driver, I want to work queue. I want to be able to, to talk to DSA directly. So then it will actually expose those work queues, and user space applications can take advantage of that and submit and complete operations from those work queues without having a user space device driver. So that's pretty cool. So how does that work with SPDK? Well, SPDK has two modes, right? The first one is our default mode, and that's where we don't rely on the kernel driver, right? And that's kind of the way a lot of SPDK community members like to, not to rely on specific kernel versions, specific kernel drivers, like to have everything in user space and directly under control. So we do have a DSA user space driver, and when you choose it, we will unbind the kernel driver from DSA and bind it to either UEFI or VFIO, and then the SPDK user space driver takes over. It initializes the hardware, it configures the hardware, it creates the work queues, right? It does all that with absolutely no reliance on the kernel driver. Now we have this other mode, right, that's supported by the DSA hardware that we call kernel shared driver mode or shared kernel driver mode. Why would you want to use this? Well, let's say you've got a situation where SPDK, the process, you don't want it to own the entire piece of hardware, right? Let's say you want to share it with either another kernel mode component that's doing some sort of kernel offload that you find valuable, or let's say you're in maybe a containerized environment or something, and you want DSA, but you can't own the entire hardware out of the cluster, right? You're only able to get, a work queue allocated to you. So in this mode, and it's pretty simple, it's how you start up the accelerator framework module. In this mode, the existing kernel driver does the initialization of the hardware. The system admin, can script the creation of work queues or, do it manually, whatever you want to do. But that's outside of SPDK. Somehow you've got to create your work queues. And then SPDK is responsible for submitting and completion operations using the same exact code as if we were using the user space driver. Same exact IO path, same completion path, same exact everything. So really the only difference between the two of these is whether you want to share the hardware with other applications or not, right? And a really important note on this is, most people when they look at SPDK and they think user space versus kernel space, you think it's a performance play, right? And that's from all the work with the NVMe Express driver and comparing our user space NVMe driver to kernel NVMe driver and all that kind of stuff. That is absolutely not the case with this. As all the performance measurements we've done between these two, and it makes perfect sense, they're nearly identical, right? Because it's just the initialization of the hardware that the kernel driver is doing. And like I said already, it's the exact same code path, not one line of code different between submitting and completing on IO, depending on which one of these drivers are used. So not a performance play, simply a use case play, to provide the flexibility that folks need. Okay, so let's talk a little bit about the roles and responsibilities of the Accel framework versus the module versus the low-level library. So some of that becomes a little bit clearer as you can make your decision whether you want to write directly to the low-level library or write to the Accel framework, or actually write a module yourself for the Accel framework and have your accelerator support an SPDK. So the framework itself, it initializes modules. Of course, it's responsible for understanding what's available to it, initializing it. It manages the opcode to module mapping, right? That table that we showed a little bit earlier. It manages task context, right? So what does that mean, right? In the typical SPDK fashion, right, we've got sort of tasks lined up through the different modules that carry context that allow us to make asynchronous callbacks in the right way, right? So mainly for Accel framework, our task context would be the callback function and the callback argument when we have a completion of an incoming operation. So the Accel framework manages all that. And of course, it submits the tasks to the modules in question. So let's look at the DSA module. What does it do? Well, it manages flow control. And this is specific to DSA, right? So DSA expects software to manage flow control. If you submit too much stuff to DSA, I think, let's say it has a limit of 128. I'm just sort of making that up. It depends on the configuration of your platform. Let's say you have a limit of 128 operations. If you try to submit 129th, you're going to get into error handling space, and you're going to kind of crater performance. So it's really something you must do when writing DSA. You never want to submit more than what it's capable of handling, so that you can continue to maintain the fast path. So the DSA module does fast path. So the DSA module does that Excel framework calls, the DSA low-level library calls. Of course, that's one of the main things it does. Submits it to the DSA library, and then another big feature that it does for you is it registers a polar for completions. Right. So if you were writing directly to the Excel framework, that's something you would have to do on your own. The DSA module will actually register a polar. It will call into the low-level library and say, hey, what do you got done for me? What do you have done for me? All that kind of stuff. Okay, now next level down, the low-level library. As I mentioned before, it discovers, initializes hardware. It does address translation, right? Virtual to physical address translation as needed. And, like most of the modules and components in the SPDK, we do as much of that as we can up front, right? So we don't do any memory allocation, and we do very minimal memory translations in the IO path. There's some cases, of course, we can't avoid it. It actually does the submission to hardware in a very optimal fashion. DSA's got some really cool low-level features for hardware submission and completion. Then it does hardware completion, and then it does something called transparent batching that we sort of borrowed from the NVM Express driver, at least in concept. But I'm going to talk about that next because it's pretty cool, and of course most of the hardware. But I want to talk about that next because it is pretty cool for a bunch of different reasons. Okay, so transparent batching. The goal here is to make most use of the hardware. And what we discovered when we first started messing around with DSA, it is really, really fast. You submit an operation, and almost before you can blink an eye, it's done, right? So depending on how your application is built, how often you need to call into DSA, you could easily find, as we did, that the hardware is never busy. It's almost never has anything to do. We're not really taking advantage of how much that hardware can digest at once. Right, we're just feeding it. Here's an IO. At some point later, we got to go do a bunch of stuff. Here's another one. By the time we get around to it, it's got one that's been completed forever. Right, so that obviously was not optimal. So we thought, well, DSA has a special operation called a batch operation, and that allows you to submit a contiguous list of descriptors in memory with one operation. So me as the DSA low-level library, if I've got a handful of operations, I can build a chain of descriptors as long as they're all contiguous, and they don't have to have anything to do with each other. They can if you want, but in the case that we're using, we don't have any correlation between these operations in the batch. And then when that batch is ready, you submit just a batch with an opcode of batch, and then the DSA will DMA that chain of descriptors in and process them all in the order in which they come in. Right, so it saves you on submission time, and it allows you to submit a whole bunch at one time. So we actually, just a bit of history here. Not only is it possible to expose this batch capability to the SPDK application, we actually did for a long time, and really couldn't find a really good use case for it. Right, the application doesn't typically know. It could, but it doesn't typically know what's really the best way to batch these things up and what makes the most amount of sense for the system performance. So we had these features. We may add them back in at a later point in time for a completely different reason, and I'll try to cover that at the very end here if I don't forget. It's not part of this talk, but it's pretty cool, and it's a big thing that we're doing next in the Accelerator framework. End of this year, beginning of next year. So we might add something like that. But anyway, it's not in the public API right now. So batching and the opcode for batching for DSA is a private thing. We use that behind the scenes to really optimize performance. So what the idea is, if we batch up single operations as they come in and then submit chains when either the batch is full, and I'll describe what that means in a second, or when the polar runs, then we actually get much better performance, both at a system level overall, and we can measure that DSA is actually busy, right? It's busy in bursts, right? Instead of little tiny single operation busy bits, it's busy in batches of the size that we've chosen empirically is 16. So what will happen is as you build up, as operations come in one by one independently from the application, we'll just throw them on this list. And as soon as that list hits 16, we submit it as a batch, and then they all start completing. And as with anything, everybody here's been doing storage for a while, right? This is coalescing, batching, whatever you want to call it. anytime that you have this trade-off, right? The more you batch, the more you save up, the more latency you are adding to each one of those individual operations. However, the longer you wait, the more latency you're adding for these individual operations. So you've got to be careful that the savings that you're getting by submitting 16 isn't outweighed by the latency that you're introducing by submitting that many. So here's a pretty simple picture, right? We've got 6 completely different operations all tied in. Let's say that these have come in and we're sitting at 6. If the polar runs, we're going to say, hey, I don't care if you get 16 or not. I've waited long enough. I don't want to introduce any more latency that is absolutely necessary. So it submits this batch of 6. However, if your application is constantly beating on DSA and you're able to fill up and submit more than 16 between 2 polar runs, as soon as you hit that 16th, it'll go ahead and submit that one and start building another batch, right? And submit that one and start building another batch. So this is the trade-off that we found, again, with a lot of empirical data, both in benchmark testing using our Excel perf tool, as well as using TCP, NVMe over Fabrics with TCP, where we use DSA to do the data digest offload, the CSC32 offload, which is a great use case for using this batching, right? Because that happens periodically, and SPDK has a lot of work to do in between the calculation of the CRCs. So it really gets a lot more parallelism in the system. Okay, so what else can you do? Get involved. And this is where I wanted to talk about the one thing that's not on the slides. You can see all the cool stuff that's happened in the SPDK framework, or the accelerator framework, right? Starting from the copy engine doing 2 things, and super simple. Now we've got 7 or 8 opcodes. We've got 3 or 4 modules, a couple work in progress. We've got these new RPCs and APIs that you can completely configure how you map operations to modules and really make this thing do exactly what you want to do. Examples in the DSA of ways to optimize interacting with hardware, that are very dependent on what your hardware is capable of doing. But what's next, right? I talked about the IPU use case, and this isn't just IPUs, but let's, imagine you want to do multiple operations on a single chunk of data coming in, right? And encryption, compression, whatever you want to, a copy, right? Copy and compress, copy and encrypt, right? Whatever combination you want to come up with, you want to be able to support that, especially and even in an IPU, right? So how would we do that today? Well, today you would do them individually, right? And although that works, it's obviously not super efficient. Especially if you have hardware, well, actually only if you have hardware that can do those in a more efficient manner, right? So if I do a copy and an encrypt in 2 different operations, that's going to use a lot of memory bandwidth, right? The copy is just going to move the data to somewhere from outside into local memory, and then the compression or encryption operation is going to have to move that data back and forth between the hardware offload that's doing that. So you're moving this data around more than you'd like to, right? So let's say you had hardware that could do like copy plus CRC, which DSA can do in one operation, right? So that way you're not copying the data and then moving the data back and forth between the engine calculating the CRC. It just does it all on the fly. Right? Well, we don't really have a good way to do that in SPDK if it's different layers in the stack that are wanting these different operations, right? If you're in one place in your code and you go, oh yeah, I need a copy in CRC, we'll just call that API and it's done, right? But what if it's 2 completely different layers? What if you want to copy the data at the top of the stack somewhere, and then somewhere in the middle of the stack you want to do compression? Well, so our idea here is we want to start building up a chain of operations and executing them at some point later in time, at the very last minute. Once you completely understand all the operations you want to do on this data, all the transformation you want to do on this data, you want to do it with the best available hardware you can, as efficiently as you can at the end of that chain. So that's what we're calling chaining. It's a pretty complex design. There's a couple slides out there. Alexi put together some stuff. I expect we'll see a lot more on this in Q4 this year, and again moving into next year. But that's a really cool, exciting, and complex feature if others want to get involved with that. So appreciate your time, everybody. Thanks for coming, and hopefully we'll see you in person sometime soon.